In the previous video, we're able to generalize A sub r for distributing r identical objects into n distinct boxes. And as for that, if you can still remember, you will have A sub r is equal to r plus n minus 1 taken r. That's the combination for that. Stands for the coefficient for your x to the power of r, which again tells us the number of ways of selecting r objects. Now, we have here additional condition that no box should be empty. In this previous illustration, again in the previous video, please try to review that if you have your time for the illustration of the formula. We actually had the consideration where possibly box 1 is not selected, box 2 is not. That's why we have a term added for that. But in this time, since we will have here n distinct boxes such that no box is empty, so if we're going to look at box 1, this is already assured and it is very guaranteed that box 1 is selected. That would mean its equivalent generated function here doesn't start with 1, because 1 means it doesn't select, it's not selected. So we'll start here with x. Selected once, x squared, selected twice, x cubed, and so on and so forth. Again, the difference from the previous video is we have 1 plus x squared and so on and so forth. We considered 1 because there is a possibility that it is not selected. So this time, since no box should be empty, so we will start with x. This is also true if we have another box, box 2. So x plus x squared plus x cubed until so on and so forth. And until you reach here, box n, your nth box, you will still have x plus x squared plus x cubed. You can see the 3 there. So let me write here the 3x cubed, so on and so forth. Okay. Now, to generalize that, we need to understand the specific equivalent expressions for this. Okay. But before we can look into that, let's try to combine all of them. So we will have n numbers. Okay. N numbers of the product of this. Or n, we are going to multiply the same expression n times. That's actually a call for exponentiation. And it will be forming like this. You will have x plus x squared plus x cubed plus dot 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 raised to the power of n. This is the shorter or the condensed way of writing the product of the generated functions representing the n boxes. Okay. Now, how do we look for a situation where x sub r will appear so that a sub r, the formula we're intending to solve, will appear in the process? Now look into this. We had a similar situation for this in this playlist where we're trying to solve for the coefficient of x to the power of k. I'm talking about there is a greatest common factor for all the terms here. That's actually x. So we can actually factor that, leaving the first term being 1, the second term is x, the third term is x squared, and all of the terms here is taken with x as a factor. Because when you do it like this is still power of n. We can now see that there is a certain function here which has an equivalent representation as one of the identities in this playlist. Okay? So with that, applying the power law, you will have your x to the power of n times 1 plus x squared plus dot 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 raised to the power of n. And again, this entire base here, the 1 plus x squared plus so on and so forth, having the sequence 1, 1, 1, 1, and so on and so forth, can be written actually as a rational expression 1 over 1 minus x. Hence, if we're going to use that here, we will get actually x to the power of n times 1 over 1 minus x, but it's actually still raised to the power of n. So we are getting closer because x is already here. They are actually presented. But in this case, take note, we are solving for a to the power of r. So we really need for r to appear. But this could be written as actually x to the power of n times, using the power law of exponent, you have 1 over 1 minus x to the power of n, which can then be written as x to the power of n times 1 minus x to the power of negative n. We're doing this because actually this one has an equivalent form as well. Using the generalization and the generalized binomial theorem video in this playlist, in the concept as well, we're able to understand that it's actually x to the power of n. We're writing the same, and you will have here this form is actually equal to 1 plus, you will have here 1 plus n minus 1 combination 1 for our x, plus you will have 2 plus, that's 2, n minus 1 combination 2 for our x squared, until you reach this type of notation, r plus n minus 1 combination r for x to the power of r. And this time, r is already here. R already is appearing. Hence, we can say that this is actually a part of our formula. Why do we not decide this to be our a sub r, since we have already a sub r x to the power of r? So it's not, because this is just a portion of this product. We still have x to the power of n here. Nevertheless, we can use this idea as concept as we reach it to that point. Using here, you will have r plus n minus 1 combination r of x to the power of r. Okay? And then again, we just need to solve for x to the power of r, and by power law, multiplication law of exponents, this could yield into r plus n minus 1 combination r and x to the power of n plus r as a combination of both. Okay, so what is next to be done here is the idea that since we would like already x to the power of r, so what if we are going to let n plus r, meaning this exponent, as simply equal to, let's say, k. Okay, let's note of that. Even if we are targeting x to the power of r, let's illustrate here k as n plus r, so that we can actually look for some relationships, because if x, we just want r, right? So using this, r could also be k minus n. Okay, so that we can substitute k in this manner. We can also this portion here as n plus r plus n being k, and this denominator being k minus n. See how it will look like. It is actually equal to, again, r plus n, or n plus r is just k minus 1. Combination here, r at the bottom with this, k minus n. You have x to the power of k now. Okay? So it's actually x to the power of k at this point now. So if this is our intended target, let's say just earlier, similar to this, but in terms of k now, so we are going to look for a sub k, x to the power of k, which again can be represented by x sub r, x to the power of r. We already have our x of power of k here. This is the coefficient of x to the power of k, which tells us the number of ways of selecting k objects, or similarly, the number of ways of selecting r objects in the given situation. So what is this equivalent to? You will have here your a sub k, pardon for changing it to k, we just simply illustrating it for r earlier, for r identical objects, but this time a sub k for k identical objects. So it's actually equal to k minus 1 combination k minus n. Okay, so this could also be used as k now stands for the number of elements to be taken, and of course your n is equal to the number of distinct boxes. And of course, this is the idea or the formula for that same coefficient, considering that no box is empty. Very different from this form of r plus n minus 1 taken r, or you can simply represent that with other letters as well. So we'll have different forms here. Now, there are also other ways to write this, because if we have, say for example, k minus 1 and k minus n, using the symmetric property for binomial coefficients, so similar also in the Pascal's triangle, this is actually equal to k combination 1, and then you have here n combination 1. The results for this, for whatever the values of k and n, are just equal or just the same. Now, why do we have this relationship? Take note, this is one of the properties, and this could also be used further. Say, for example, if you don't want this formula, this is also another formula for your A sub k. Again, a number of ways of selecting k objects. That's it for this, and we have already the formula. Again, as mentioned, our formula earlier was transformed into k. A sub k is equal to k minus 1, or taken k minus n, or k minus 1 combination n minus 1. Thank you very much for watching.